Okay, hello and welcome everyone. This is going to be another two-parter, but this is certainly going to be a longer video. We have a lot that we have to cover. As I've stated before, this is very, you know, definition heavy material. So there's a lot that goes into this. So you need to pay attention. You need to make sure that you write everything down. Firstly, we're going to look at the universal systems model and what all it entails. So the universal systems model, input, process, output, and feedback help users isolate the components of a system so that they may be properly used and maintained. So we try and build everything around the same ideas under kind of the same process, so that way it doesn't matter, kind of where you fall in the ranks. You can systematically kind of approach any kind of technology and work your way through it. A system is a group of organized parts or subsystems that are integrated collectively to achieve a desired goal. All systems have various inputs which go through the process to produce outputs. Again, so it's input, process, output, and then finally feedback. So a high-functioning system collects feedback to increase efficiency. So systems can fall into kind of two primary categories, which is simple and complex. You will get, you may run into some things that kind of fall in the middle of them, but overall they are still categorized as simple or complex. Simple systems have a limited amount of subsystems which can be easily identified and diagnosed. So, example, pens, mechanical pencils, bikes. Okay, complex systems have an hierarchy of subsystems which often interact with the environment and or unknown variables. I am not aware of a specified cutoff to qualify something to be simple or complex, but just kind of be mindful of those terms. So some examples: water cycle. Complex system could be cars, or it could also be traffic. Analyzing traffic patterns is a big area in mathematics right now. So types of systems: you have biological systems, or groups of organs that work together to perform a task. So like the hearts, the brain, cardiovascular systems, neural systems, just the body in general. You have mechanical systems, a system of mechanisms used to use power to change force or movement. So thermostat, bicycle, cars. A lot of when we think about technology, we're actually thinking of mechanical systems. Ecosystems, a group of organisms that interact with their natural environment. And so example, predator-prey, nature. You have ecosystems within nations, and then you can even have sub-ecosystems within those nations. It's just very, very complex. Social systems, how organisms interact with the design world, such as supply and demand or driving. So there's that traffic coming into play as being a complex system. And so now let's talk about those individual components. You had your input, your process, your output, and your feedback. Inputs consist of the resources that flow into the technology system. So inputs include people and time, the material and capital, tools or machine energy, and information. So it's kind of what starts the initial drive within a system. And so when I'm talking about these, think large scale. Think about things like economy or an entire industry. When I'm talking about these systems, I'm not talking necessarily about an individual item. Okay, I'm talking on a much larger scale on these. Processes consist of purposeful sequencing of the tasks that combine resources to produce a desired output. Processes can be categorized into problem solving, processes that involve identifying the problem and selecting a solution. This is where mathematics comes into play. The better you are at math, the better you're going to be at problem solving. That's just one of the areas where mathematics come into play. Production, process that involves creating a product or structure. Oh, guess what? Math comes in there too. Management, process that controls and manages the inputs and processes involved into a system. Oh, guess what? Mathematics pops in there. You might be noticing a bit of a trend there. If you want to know more about how they become involved, feel free to ask. Output is the end result, which can have either a positive or a negative impact. Now, it doesn't necessarily mean that it's positive or negative exclusively. You can always have blends based off of what was going on. Outputs can take the following forms. Unexpected desires, you know, the happy accident. Oh, wow, look at that. Look at that. You know, Silly Putty. Silly Putty was actually originally designed as a tool to help astronauts keep from losing papers in space. And it's turned into, you know, it's turned into a toy for, you know, for kids of all ages. Then you have expected desire. You know, this would be like, you know, when you're producing a car and you want people to buy the car. People do buy the car. That is exactly what you wanted it to happen. Unexpected, undesired. Okay, this is the Arch Deluxe from McDonald's. Okay, they were hoping that it would take off and do really well, but it did terrible. Nobody bought it. And, you know, and so that's obviously an undesired consequence there. And then expected undesired. This is when, you know, this is when something is intentionally done where the outcome isn't necessarily favorable. It's rare that you go into a project this way with an expected undesired. Usually that's something that kind of transitions over in the future. Now we talk about feedback. Feedback is information used to monitor and control a system. So this is, you get your results, and then from those results you determine what to do next. The feedback loop allows the system to make necessary adjustments during the operation of the overall system or the specific subsystem. So that is a more formal way of saying what I had just said, which is you get the information and then you can adjust accordingly to make sure that everything is operating properly. Open systems do not have a feedback loop and require human intervention. Example, a microwave, which requires the user to input the appropriate time and determine if the food is prepared. If you cook the food too long, there is nothing in a standard microwave that tells it to stop. Or if it hasn't been cooked long enough, there is nothing in the microwave to tell it to stop, or to tell it to keep going. There are some super fancy microwaves that are starting to come out now that do have that kind of feedback loop. But most of the time, the feedback loop involves a person to check to see whether or not it's done. Closed systems apply feedback and manage to control the system. So example, a home heating system, which requires the user to input a desired temperature, uses a thermostat to collect the feedback to turn the system on or off. Now, I have a system in my house that actually ups the ante a little bit, because I put in a temperature range, and if it detects it's going too hot, then it turns on the AC. If it gets too low, it turns on the heat. And so that would be an example of a closed system. And then there's systems theory. This stuff gets really awesome. It gets really awesome. Systems theory is the study of how to make things work and suggests that both natural and man-made systems have interrelated parts that work together to produce an output. All systems tend to have similarities in the way they work. That's that universal systems idea. And the application of systems theory can be applied to the engineering design process. Again, this is a lot of information in here. If you have any questions or would like to know further about any specific point in this lesson, feel free to give me a shout. Otherwise, you know, the next part of the video is coming up, and I hope that it's heavy. Okay. There's a lot of stuff coming up in the next part of this video. But I hope it works well for you, and we'll see you in the next video. Hello, and welcome to the second part of this video. So there is a lot of information here. We are talking about the electrical systems, electrical fundamentals today. This is probably my weakest element when it came to the engineering, because so I had a class on it. I had a class on it in college, but I was also an aerospace major, and so while I understand a lot of the basics and you know, passed the class successfully, a good friend of mine that was actually on the clogging team that I was on, she was an electrical engineer. And so I relied on her very heavily to help me through this one. because there's just so much stuff. And this was her specialty. She loved it. And what I can gather, it seems like either you just absolutely love this material, or it's one of those that you just kind of have to suffer your way through it. It's incredibly fascinating, especially, you know, I've had to do work on my own home, and so I get very nervous with electricity because I know the damage that it can do. But some of the stuff that happens within it is really, really cool. And so when I get in and work on my computer and stuff like that, you know, I really do like it. It is entertaining, but it is very, very, very easy to get lost in all of this because it is so specific. And if you mess up, and you know, you can potentially ruin everything that you were working with if you short the entire board. So it is precise. You have to pay very careful attention to it until you get good enough that you can learn to build in, you know, redundant safety systems and things like that. So what is the purpose of this? By understanding electrical fundamentals, you'll be able to manipulate and control electricity to perform tasks. Okay, being able to control how the electricity is going to go is an amazing thing to me. I love it when I've worked with robotics, you know, that I plug everything in and then all of a sudden it starts working. That is really cool. But again, you have to be very careful with it because if you reverse something, if you cross the wires, you know, then stuff very bad can happen to it. You know, I'll tell you this story and then I'll just move on. I will never forget it. As a kid, I remember. I mean, gosh, I would have been, you know, 3 or 4, and this memory is still very vivid in my mind. My neighbor came over and asked help from my dad because his car battery had died, and so my dad offered to, you know, to go and help jump the car. And if you don't know what we mean by jump the car, it's where you connect 2 cables to the batteries, and you use the one vehicle to kind of charge the battery in the other. And I remember I wanted to go over there and watch him do that, and but my mom wouldn't let me. And I remember hearing my dad's truck crank up, and then wasn't too long after that, I remember hearing this boom that was like a cannon going off. I mean, it was just loud. It scared the living daylights out of me, and I'm sure it scared my dad and my neighbor. I'm sure it scared them as well because they were a lot closer to it than I was. And what it was is they had crossed the cables. They had a positive lead going to a negative end and a negative lead going to a positive end. And it blew the battery. And by blew, I mean an explosion. An explosion. They ended up actually having to ditch the truck because of all the damage into the motor. And, you know, the plus side to it was the truck needed to be ditched anyway. But yeah. Electricity, you have to be very careful with it. To this day, I still plug my ears whenever I've had to jump a battery because it just makes me so nervous. So, you know, hopefully you'll never experience anything like that, but just be mindful that this can be very dangerous stuff when you're working with it. All electronic circuits have a path for electrons to flow and an energy source. So I remember being told, think of electricity, think about it like water flowing through a river. You know, it's when we talk about current, think of a river current, because instead of water, think of electrons flowing through, just kind of like a stream. Electrons will flow from the negative to the positive. Electrons have a negative charge. If you remember back in that lesson from thermo, you know, heat always goes from the source to the sink. Positive means that there are fewer electrons, and negative means that there's too many electrons, or that there's an abundance of electrons. So the electrons will always go from the negative, because there's more of them, towards the positive. The amount of electron flow will depend on resistance. Direct current, or DC, electrons flow in only one direction. So examples of this are the battery, and pretty much anything that operates on a battery. So handheld electronics like an iPod or an automobile. Basically anything that you do not plug into the wall. Okay? So the electrons move from the negative end towards the positive end. Then you have alternating current, or AC, which, you know, AC and DC, you might know where I'm going with that one. So thunderstruck all the way. Electrons flow back and forth, negative to positive, back to negative. Or it's the alternating current. Okay, these are electrical appliances in the house. Pretty much anything that you're going to, that you plug into an electrical outlet. And it has to do with how the power is generated from these as to why it goes back and forth. DC was Edison, AC was Tesla. All right, so how does this work? We're going to be jumping into chemistry for just a little bit here. We got to talk about we're going to talk about the atom. This is the Bohr's model of the atom. The atom is made of 3 subparticles: the protons, neutrons, and electrons. Each of those have their quarks and subparticles, but we're just going to stick with these. So the electrons is what carries the electrical charge that we are used to. Protons give the positive charge, neutrons a neutral charge, and electrons the negative charge. The electrons rotate around the group of protons and neutrons. When the electrons move from one atom to the next, that is called electron flow. Opposite electrical charges always attract, and like electrical charges always repel. So, when 2 electrons, push up against each other, they tend to push each other apart. And what you like to have is a positive and negative, and then they will tend to go together. Balanced atoms normally have an equal number of electrons and protons, which means they're electrically neutral. They can have as many neutrons or as few neutrons as they want. But what you're looking for, like in the case of this atom, would that be lithium? I'm trying to remember. I might be too high on that one. But there's 4 protons, there's 4 electrons. Okay, and so for stability purposes, that's what you want. Ion particle occurs when an atom loses or gains an electron to cause an imbalance. When an imbalance occurs, ions will take or release an electron to try and become balanced again, causing this electron flow. Ions can be charged. You have a positive charge, which means that there is at least 1 less electron than proton. You can have a negative charge, which means that there is at least 1 more electron than a proton. The positive ion attracts the negative ion to become balanced. So salt water, sodium ions are missing an electron, which gives it a positive charge. This makes salt water a better conductor than fresh water. Electrons rotate around the atom at different orbits. So bound electrons orbit around the nucleus on the inner rings, and free electrons are loosely held and orbit around the outermost ring, which is known as the valence ring. So if you've ever heard about valence electrons, they're the ones on that outer ring. There is actually a specific pattern as to that. There's 2 on this innermost ring. There's 8, and then if I remember right, I think it goes up to 16 on the next one. But that's going to be more for your chemistry class. I won't go into that one. An insulator is any material that prevents the flow of electrons. Insulators typically have 5 to 8 free electrons in the outer ring, which means they are tightly held to the atom and do not easily move. Insulator materials include glass, rubber, and plastic. A conductor is any material that easily allows their electrons to flow. So conductors typically have 1 to 3 free electrons in the outer ring, which means that they are loosely held to the atom and can easily move. Easily move is key there. Conductor materials include copper and gold. Silver is also a good conductor. A semiconductor is neither good. It's not a good conductor or really an insulator. Semiconductors have exactly 4 free electrons in that outer orbit and are commonly used to manufacture diodes, transistors, and integrated circuit chips. Semiconductors include carbon, silicon, and germanium. Ohm's law, very important when talking about electricity. proposed by George Ohm is the relationship between voltage, current, and resistance. When you get into electricity, you're going to hear those terms tossed around like crazy. Ohm suggested that if you double the voltage across something that provides resistance, then the current would also double. And so we come up with this equation: voltage is equal to current times resistance. Voltage represented by V, current represented by I, and resistance represented by R. I don't remember exactly why current was labeled as I, but it just is. So what you end up with is V equals I times R. This is multiplication, not the letter X. Voltage is the electrical force that moves electrons through a conductor. Voltage is electrical pressure that pushes the electrons. So you can think of it as you can think of it in kind of in terms of pressure. Current is the quantity or the flow rate of electrons moving past the point. Current flow is known as amperage, or amps for short. Voltage is measured in volts, and current is measured in amps. Resistance is the force that reduces or stops the flow of electrons and imposes voltage. So resistance, again, going back to a stream model, resistance can be thought of as anything from a lot of rocks in a stream to to possibly even an entire dam that is there to try and stop the water from flowing. So in a series circuit, the current through two or more resistors is the same, and the circuit is connected in a series. And so what we mean in a series circuit is that everything has to follow essentially this one major path here. The total resistance of the collection is the sum of the individual resistances. In series, electrons have only one path to follow to complete the circuit and must travel through all components. Okay, that's just what I said. In resistance, I don't know if I mentioned it earlier, resistance is measured in ohms. And so I don't know if you can see it here, but there is the letter omega that is used to represent ohms. Okay, so this series, the 3K, so it's 3,000 ohms. This one, to measure its total resistance, that's a 1 right here. So it'd be 3 plus 1, which is 4, plus 2.5, which is a total of 6.5. So to travel this circuit, it would be the same as passing through one single resistor of 6.5 thousand ohms. In a parallel circuit, the voltage through two or more resistors is the same and the circuit is connected in parallel. So what that means is that it can pass through different, the electricity can flow through different points. So the total resistance is the collection divided among the three resistors. This is harder math to do. So I'm not going to do that example. I'm not going to do that example here. In parallel, electrons have multiple paths to follow the complete circuit and do not need to travel through all components in order to do so. So in other words, the electrons can pass through this resistor or this final resistor here, but they do not have to pass. They do not have to pass through all three. Okay, so this is an experiment that I would love to do in this class, but unfortunately we're not going to be able to since we're in remote. But it is really neat to be able to watch how all of this works. So in just a typical kind of basic electronics kit, you can see you can see the different kind of components that would be in it. That is this slide. Now here is where this is where it gets just really heavy. electronics systems are often put up in diagrams. They're put up in diagrams. And so you have these different symbols, and those different symbols tell you what, essentially what goes where. I'm going to be nice. I'm not going to make you learn all of them. Okay, but I am going to expect you to know just a couple. Just a couple. So the diode, I want you to know the diode. The resistor, so the push button, I don't see the switch here. Push button, which is a type of switch. The battery, and then the ceramic disc capacitor. Okay, those are going to be the ones that you need to, those are going to be the ones that you need to focus in on. Okay. All right, so this is getting all jumbled in here. So don't worry about this one, because this is these are the different kind of resistors that would be introduced within a particular pack. But you do want to pay attention to this one. Okay, all resistors have 4 color bands on them, which is the color code. So you have the first and second digit, which are the first and second bands. Then you have the multiplier, which is your third band, and then finally your tolerance. Okay, and the gold band is a 5% tolerance. The silver band is a 10% tolerance, and then if there's no band, it's a 20% tolerance. And so you can always, whenever I look at them, I use the tolerance band to kind of help me determine which direction that I need to go. And then you can just kind of follow this chart here. So they use colors to represent the numbers. They use colors to represent the numbers. And so in this case, so you have a red and orange, so that's a 2 and a 3, so that's 23. And then the multiplier down this way, so white would be no multiplication, so white would not be used at all. Black would just be multiplied by 1. But this is yellow, and so yellow is 10,000. So it's 23 times 10,000, so that's 230K ohms would be how that one works. If you've ever been able to use these, this is what's called a breadboard, which just help you combine several electronics. It helps you connect a lot of electronic pieces without having to get in and solder all of those pieces individually. So it has the 2 sides, A through E, and then the ditch, and then F through J. The holes are connected in the rows, not in the columns. So if you can see over here, there's numbers down the left and right hand side, and so it's the rows that make the connection. So if you're trying to sync up if you're trying to connect a lot of pieces, you use it in the rows, not in the columns. If you use the columns, A through E, to try and make certain connections, then what you're making is cross connections, which you really have to understand you really have to understand what you're doing here. Okay, so this is just a simple circuit. Here is your battery. The negative end is here, so the charge is going to flow from the negative end down through the resistor and then across back over to the positive end. This is a 9-volt battery, and then the resistor is 1,000 ohms. So let's go back and look at what this capacitor. So we know the answer. It's 1,000 ohms. So let's go back up here. Brown, that was 1, and then it was black, which is 0. So that means that it's a 10. Then the multiplier is red. The multiplier is red. So it's 10 times 100, which is 1,000. And then the resistor was gold. And so gold means that this has a 5% tolerance. So it can be higher than 1,000 by as much as 5%, and it passed the quality control, or it can be lower than 1,000 by 5%, and it passed quality control. That becomes really important when you're trying to get stuff to, when you're trying to get stuff to work, and you want to make sure you don't short it, and you don't want to short it out. All right, so all of this though is going to get into, this is using multimeters. We're not going to do that. So this slide is here if you want to read it, but we're not really going to be able to get into that, unfortunately. And I would love to get you into some more of the math behind this, but that is just going to be outside of the scope of what we're doing, of what we are doing right now. So, here's another slide that's just kind of there. It's kind of for your interest, but really, for my concern, by the time you get to here, my expectation would be, could you read just a simple little diagram? In other words, could you identify that this is the battery, this is the resistor? If I had a diode on there, would you be able to see that? If I had a capacitor on there, would you be able to see that? Could you, given an image like this here, be able to tell me how many ohms resistance it would have, and that sort of thing? And as far as the math component, that's about as far as I'm going to take it. That's about as far as I'm going to take it in here. I'm not going to worry about getting total resistance on series and parallel circuits and stuff like that. That's more for physics or another class. Okay, so I hope that you enjoyed this video. If you have questions, as always, feel free to ask me. Otherwise, we'll see you in the next one.